Hello and welcome to my new lecture. In this lecture I am going to talk about topic 20.6, 20.7 and 20.8 of the Fundamentals of Physics book by Halliday Resnick Walker. And these topics are entropy in real world engine like refrigerator, efficiencies of real engines and statistical view on entropy. First of all, I would look at topic 20.6, that is entropy in real world refrigerators. A refrigerator is a device that uses work to transfer heat energy from a low temperature reservoir to a high temperature reservoir. This is continuously done by a series of thermodynamic process. In case of a refrigerator, the compressor uses its work done to transfer energy from the food storage compartment, which is a low temperature reservoir, to the room which is at a high temperature reservoir. This shows that in case of a refrigerator, electric compressor is used for doing work, and air conditioners and heat pump are also refrigerators. In case of an air conditioner, the low temperature reservoir is the room which we want to be cooled, and the outdoors are high temperature reservoir. In case of a heat pump, the room is considered high temperature reservoir, and outdoors are considered as low temperature reservoir. Heat pump works in reverse of that of air conditioner. Thus one can say that the refrigerators are in operation opposite to that of an engine, because in case of engine, the heat energy transfer takes place from high temperature reservoir to a low temperature reservoir. For the case of a refrigerator, the transfer of heat energy takes place from a low temperature reservoir to a high temperature reservoir. Now let's look into the definition of an ideal refrigerator, just as we looked into an ideal engine. In case of an ideal refrigerator, all processes are reversible and no wasteful energy occurs as a result of turbulence or friction. So just like an ideal engine, there is no wastage of energy and all processes are reversible in case of an ideal refrigerator. I would like to make the schematic diagram of a refrigerator like we did for the case of a heat engine. Let's say this is my high temperature reservoir and this is my low temperature reservoir. And work is done over here. Now QL heat goes from this low temperature reservoir and working substance works on it and sends the amount of heat energy QH to high temperature reservoir. For the case of a refrigerator, this working substance would be a compressor, and for the case of air conditioner and heat pump, they will change. You can see many differences between this and a Carnot engine. In case of a Carnot engine, the work was done by the system. However, in case of this refrigerator, work is done on the system. And transfer of heat energy was from high temperature to low temperature reservoir in case of a heat engine, and in case of a refrigerator, this heat energy QH is from working substance to high temperature reservoir. And in case of refrigerator, this amount of heat energy QL is from the low temperature reservoir to the working substance. So this looks like a reverse to a Carnot engine, and it can be said as a Carnot refrigerator. Now to calculate the coefficient of performance for this Carnot refrigerator or a refrigerator represented by K, and same as efficiency, this would be equals to what we get or what we want, or output divided by what we pay for. What we want in this case this QL to be as much large as possible, because this is the transfer of heat energy from low temperature to high temperature. That is what we want. We want this to be maximum. And so in numerator of this expression should be QL, and what we pay for this working that is done on the system. For the case of a refrigerator, it's a compressor, and what we pay for should be work done on the system. Now for the case of, as this is coefficient of performance, it is given by Kc. Now this Kc should be QL over, since work done is the difference between QH and QL, I can write it down like this. And for the case of temperature, as temperature and this heat energy would be an analogous quantity, in this case this would be TL over TH minus TL. Let me call this as equation A, and this is my equation B. This is the efficiency of an refrigerator. The values of K is typical values for K are 2.5 for the case of a air conditioner, and Kc for the case of a refrigerator is 5. However, these values can vary due to different climatic conditions and the temperature of the outdoors and the low temperature reservoir. So these values can vary. However, these are typical values for air conditioner and a refrigerator. Moving onward, I would like to elaborate what should be a perfect refrigerator. A perfect refrigerator would be one which requires no input of work to take the heat energy from a low temperature reservoir to a high temperature reservoir. One can say that it's an inventor's dream. However, in the form of a schematic diagram, one can say that a perfect refrigerator would have this low temperature reservoir and this high temperature reservoir, and like this. It takes this amount QL and sends this heat QH to the high temperature reservoir. This would be a perfect refrigerator, as it requires no work to take this heat energy from this low temperature reservoir to a high temperature reservoir. For the case of an perfect refrigerator, there would be no change in heat energy as it moves from the low temperature reservoir to a high temperature reservoir, because there is no working substance involved in this whole process. So for the case of a perfect refrigerator, I can write it down as QL is equals to QH is equals to Q. So rather than giving them name as QH or QL, I would say that Q amount of heat energy is transferred from low temperature reservoir to a high temperature reservoir without any working substance. The entropy of this system can be represented as the entropy of this cold reservoir would be minus Q over TH. This is negative because heat is this is positive because heat is added to cold reservoir or high temperature reservoir, and the entropy due to this low temperature reservoir would be Q because same amount of heat is transferred and this is temperature is TL. So this is our change in entropy. Since we know that this TH is greater than TL, high temperature reservoir has temperature greater than the low temperature reservoir. If we substitute or look into this result and put it in it, then we would see that delta S under this scenario would be a negative quantity. This means the change in entropy decreases for a perfect refrigerator, and this is against second law of thermodynamics, because according to second law of thermodynamics, delta S is always greater than equal to 0. So this result violates second law of thermodynamics, and one can say that perfect refrigerator does not exist. This implies that perfect refrigerator does not exist. This leads to another very important result, that no series of thermodynamic processes exist whose sole purpose is to transfer heat energy from a low temperature reservoir to a high temperature reservoir. There is no such refrigerator which takes heat energy and sends it to a high temperature reservoir without the involvement of a working substance. Next is our topic 20.7, efficiencies of real engines. Suppose I consider an engine X whose efficiency is given by this epsilon of X, and I have a Carnot engine whose efficiency is given by E sub of C. And in this section we want to prove that no heat engine has efficiency greater than the Carnot engine. To prove this, I would contrarily suppose that this X engine has efficiency greater than the Carnot. I have taken this to be my claim. If my claim goes wrong, it means that Carnot engines have the maximum possible efficiency. So I have supposed on contrary that there exists an engine X whose efficiency is greater than the Carnot engine. Let's say this is my high temperature reservoir and this is my low temperature reservoir, and this is my engine X. Engine X takes this energy QH from the high temperature reservoir and sends it the QL energy to this low temperature reservoir, and the work done by this engine is used to operate a refrigerator. Work done by this engine is used to operate this refrigerator, which takes QL and sends this energy QH to higher. To differentiate these two, I take this value as Q dash of H and Q dash of L for the case of an engine X, and for the case of a refrigerator I take this value to be QH and QL, and the process, thermodynamic process, goes like this, right? So the work produced by this engine X is used to operate a refrigerator because it provides it with the necessary work that is required to move this energy QL to QH. We have to also keep in mind what a ideal refrigerator is. In case of an ideal refrigerator, this is high temperature reservoir, this is a low temperature reservoir, and it sends the amount of energy Q without any working substance to the high temperature reservoir from the low temperature reservoir. As we suppose that the efficiency of the engine X is greater than the Carnot engine, so this leads to work done per unit Q dash of H must be greater than W over Q of H. Since efficiency is work done what we want over what we pay for, so this result leads to this result. This implies that because work done is the same, this implies that QH must be greater than Q dash of H. Heat energy transferred to a Carnot high temperature reservoir should be greater than the heat energy transferred to a engine X high temperature reservoir. Now the work done by the Carnot engine X engine and the engine X is same. This say that work done for an engine X is Q dash of H minus Q dash of L, and since it is equal to work done by a Carnot engine, which is Q of H minus Q of L, and we have noticed that this Q of H implies that Q of H, I take it over there, minus Q dash of H should be equals to Q of L minus Q dash of L. Just doing a bit of mathematics on this equation. Now we know that Q of H is greater than Q dash of H, so this must be a positive quantity, and since it is heat, I write it down as a positive heat Q. Once again I repeat, I have already written over here that this QH is greater than Q dash of H. This means the subtraction of these two would represent in a positive quantity. You can also see from this inequality that Q of H minus Q dash of H should be greater than 0. That's why I say that this Q should be a positive quantity. Q should be positive. These results, if I elaborate them with this diagram, show that the work produced by this engine X is used to run this refrigerator. So no extra input of work is required to take this heat energy from low temperature to a high temperature reservoir. When no external work done or W is 0 for this case, this basically represents a perfect refrigerator. This represents a perfect refrigerator because the work done produced by this system is used by this refrigerator. So no external input of work is required in this case. This is same as a perfect refrigerator. However, according to second law of thermodynamics, no perfect refrigerator exists. At one stage we are saying that a perfect refrigerator exists, but according to second law of thermodynamics there is no perfect refrigerator. It means our supposition is wrong, our basic supposition is wrong that the engine X has efficiency greater than the Carnot engine, and we must change it to that the engine X has efficiency less than the Carnot engine. So the maximum possible efficiency of any engine is its efficiency given by Carnot. No other engine has efficiency equal to or greater than the Carnot engine. That's what we wanted to prove. In the next section, that is 20.8, and the last topic of this chapter, that is a statistical view on entropy. In this section, we would look into the statistical mechanics that is involved when the number of molecules fill the states which are known as microstates. How many ways or how many arrangements are there to fill these molecule spaces. Let's say I have a box which has two parts, and they are insulated from each other, and I have 6 gas molecules. All of these 6 could be in this section of box or in this section of box. There is a possibility that 1 are here, 5 are here, or 5 1, 4 2, 2 4, 3 3, or 2 4, 4 2, or 1 5, 5 1. So there are 0 6. So there are many possibilities of these molecules in these boxes. And I want to basically calculate how many ways are there for the molecules to reside in these spaces. And one thing I have to notice is that molecules are indistinguishable. This means that I cannot differentiate between the molecules. So the order will not be important in this case, as molecules are not distinguishable. Now if I suppose that I have 4 molecules in this portion of the box and 2 molecules in this portion of box. So the number of ways of arranging these 4 molecules would be 4 factorial, right? Or you can say that 4 into 3 into 2 into 1 is 24. So these are the number of ways of arranging these 4 molecules in this portion of the box. And it sounds very reasonable because the number of ways of arranging this molecule is 4, and once you have arranged this, you have 3 molecules. The number of ways of arranging these 3 is 3, and now you have 2 fixed, and then number of arranging this molecule would be 2, and last one would be 1 way. So total ways of arranging these 4 molecules is 24, or you can say it as n factorial, right? And number of ways of arranging these 2 molecules is, since they are 2, this would be 2 factorial. 2 into 1 is 2. Now since there are 6 molecules, the total number of ways of arranging all these 6 molecules should be 6 factorial, which comes out to be 6 into 5 into 4, 720. Now the number of ways of arranging these 4 and 2 molecules would be known as multiplicity. This is known as multiplicity factor, and it is represented by W. And W would come out to be 6 factorial over 4 factorial over 2 factorial, which comes out to be 15 in this case. This means that there are 15 independent microstates, 15 independent microstates. So one can calculate the number of microstates for any number of molecules. Now I generalize the result. Let's say I have n molecules, right? N1 are in one way or in one form, N1 are in, let's say, one state, number of molecules in one state, and N2 are in second state. So they could be n3 or n4. To calculate the multiplicity factor W, or the number of microstates that are possible, should be equals to n factorial over n1 factorial into n2 factorial. So this is the way of calculating the number of microstates. And according to statistical mechanics, all microstates are equally probable. Means having in this case the configuration of 0 6 6 0 1 5 5 1, right, 4 2 2 4 3 3, all these microstates are equally probable as per statistical mechanics. However, looking into these results and the calculation of factorial as the number grows larger, since these are 6 molecules and you have millions and billions of molecules, gas molecules, so calculation of factorial of numbers greater than 100 results in an infinite result. So it would be difficult to compute using this formula the number of microstates when you have large number of molecules. To overcome this, we would include the probability and to calculate the entropy, we would basically use the concepts of probability, and let's see it in under the heading probability and entropy. And the entropy is given by Boltzmann entropy equation. When you have this multiplicity factor W, you can calculate the entropy by K natural log of W. This is known as Boltzmann entropy equation, where K is Boltzmann's constant, and this Boltzmann constant is given as 1.38 into 10 raised to power minus 23 joule per Kelvin. Its value is this one. Now the problem that I discovered earlier, that to calculate the factorial of large number becomes almost impossible when you have more than 100 molecules. Then factorial of 100 we give is infinite. So to overcome this problem, one can use the Stirling's approximation to overcome this issue, and this gives that natural log of n factorial is n natural log of n minus n, or n into natural log of n minus 1. So when you have large number of molecules, the natural log of these would be a lesser quantity, and you calculate it via this one, right? This would make it a lesser value, and you can calculate the number of microstates using this Stirling approximation. To further enhance our understanding of today's topic, let's do a numerical. This is numerical number 37 of the book. A Carnot air conditioner takes energy from the thermal energy of a room at 70 degree Fahrenheit and transfer it as heat to the outdoor, which is at 96 degree Fahrenheit. For each joule of electric energy required to operate air conditioner, this air conditioner, how many joules are removed from the room? So looking into this numerical, I see that the low temperature reservoir has temperature at 70 degree Fahrenheit, and this is low temperature reservoir, and high temperature reservoir is at 96 degree Fahrenheit. And I can calculate the efficiency of this before calculating the number of joules required from the room. This efficiency of this would be equals to TL over TH minus TL, and this would be 70 over 96 minus 70 is 26, and this nearly comes out to be equals to nearly 2.68 or 69. This would be its efficiency. Now to calculate how many joules are removed from the room, the efficiency is given as, in terms of heat energy, QL over QH minus QL. And since I know this efficiency to be nearly equals to 2.7, this means 2.7 QH minus 2.7 QL should be equals to this QL, and the QL should be equals to, it would add up over here, it would become 3.73, and this would be 3.7 over 2.7 QH. This much energy is required per joule to transfer it from a low temperature reservoir to a high temperature reservoir. Hopefully you have understood this lecture. In this lecture I have discussed in detail the refrigerator, what is a perfect refrigerator and its efficiency, and no heat engine has efficiency greater than the Carnot engine. Then we have looked into the statistical mechanics and how it is related with microstates, and how to calculate the entropy in terms of these microstate, and in the end we have done a numerical related to this topic. I will be back soon with another lecture. Thank you.